Hi everyone, welcome to this week's ESIG seminar. Before we begin, I'd just like to give an overview of the structure of the seminar today. So we'll have a talk for 40 minutes. We're going to have questions at the end, so please keep your mics muted throughout the whole duration of the talk. Just so everyone is aware today that the talk is being recorded and live streamed on YouTube. To ask questions at the end, please either raise your hand or type your question in the Zoom chat and we'll read out your question for you. For the audience joining us on YouTube as well, you're also welcome to ask questions via the chat on YouTube and we will read them out on your behalf. Today we're very excited to introduce all of you to Dr. Maren Brehme, who is joining us from Switzerland this afternoon. Maren will talk to us about perspective on sustainable development and operations of geothermal systems. Maren completed a Diploma of Engineering in Hydrogeology at the Technical University of Berlin. Afterwards, she took up the role as a research scientist at GFZ, a German research center for geosciences in Potsdam, where she worked on groundwater flows and geothermal exploration and operations. Alongside this, she obtained a PhD from the University of Göttingen in Germany, with the focus of her work being on the role of fault zones on structure, operations, and prospects of geothermal reservoirs, a case study in Lahandog, Indonesia. Maren then went on to do a postdoc until 2019 with the Research Center in Potsdam, where she researched the topic of stimulation for enhancing geothermal systems. Upon completing her postdoc with GFZ, she then went on to become an assistant professor at the University of Technology in Delft, in Netherlands, where she continued her work within geothermal engineering with a focus on geofluids applications. During her time at Delft, Maren was awarded a very prestigious grant as a PI for the International Training Network of the EU Marie Skłodowska-Curie Action. This €3.5 million grant enabled her and her colleagues from 4 league universities of Delft, Aachen, Milano, and Zurich to open up 13 new PhD positions, with the sole focus of the research to be on efficiency and safety in geothermal operations. Maren is now carrying on her pioneering work with the geothermal space from ETH Zurich in Switzerland. So thank you so much, Maren, for joining us. We are very thankful and grateful for having you on our seminar series. So without further ado, I'll now pass you over to Maren.
Oh, thank you, David, for this nice introduction, and thanks for having me this afternoon. I'm really excited to speak here to you and to share my knowledge, my experience in geothermal energy research, and I all invite you that we have a really vital discussion afterwards, and that you also ask questions in between or whenever they pop up. So let me start share my slides and hope you can see that. So I will speak on the perspectives on sustainable development and operation of geothermal systems, and David already introduced some of my research topics. They can be maybe summarized in 2 questions, which is where to drill the next well and how to operate sustainably, which affects the efficiency and the safety. The worldwide power generation is still dominated by hydrocarbon sources. So we have to make a big move here to increase the renewable energies. And also within renewable energies, geothermal still plays only a small role. And I'm here to change this. This is my agenda of research. The top 10 geothermal countries, this is a bit not that much outdated, but from 2019, it were the US, Indonesia, Philippines, Turkey, and New Zealand, the top 5 countries producing geothermal energy. And these are also countries where I do my research in. So also with doing research abroad and collaborating with that countries and universities and companies in that countries, you can learn a lot also for the Central European market and future opportunities. So these are the two topics I will cover today. I will introduce you to your different research projects I have been leading, I've been involved in, and of course I don't do that on my own, but I have a team who is with me and several more people who were with me, but these are the current faces working together with me in different places in the world. They are all located at ETH Zurich at the moment. They are master students, most of them PhD students, but also postdocs. And we work on topics like drilling success, efficient operation, and also safe operation. I want to start and motivate a bit my research with this field in Indonesia. It's called Lahenda. It is one example I studied, and where I saw a very clear trend where we see the drilling success in geothermal energy, which is only about 50%. And this is one specific field, but you can take this as just an example for the worldwide statistics, which I show you later on. So you see a map with just a topographic map with the lake in the middle, 2 small villages, a few roads, and then you see also well clusters, which will pop up on the right side. You see the statistics of the drilling success for these wells drilled in this field. So we have a well number, which is basically by time. So they drilled up to 30 wells until today. And then you will see popping up the output of that well in megawatt electricity. So we are in high enthalpy reservoir producing electricity in that field. So let's start. The first well was drilled basically to the west of this system, and it had no output. So it was a dry well, what we call them. A second well more to the north, also that one was dry, therefore black. And then a third dry well was drilled in the very north of this map. And also that one was dry and had 0 output. From then on, the operators, or at that time, license owners of that field, moved further south, and they were more successful. The fourth well had an output of about 7 megawatt electricity. The fifth well in the central to the east of the system also had a little bit lower, but still quite good output, so 5 megawatt electricity for that well. The sixth well in the southeast, no output again. Also number 7. Number 8, again, a bit of output, and I will not bore you with every single well, but that's the rest of the story. So we have about 30 wells in that field, and you see the black wells have no output, so they have not been successful drilling that wells. 0 output for about half of the wells that have been drilled here. And if we consider drilling a kilometer of well depth, €1 million basically, we spend a lot of money here for nothing. Basically 50% of the costs were for nothing. They can't use these wells either for injection, production, or monitoring, but half of the wells were still productive. And you see 2 green wells, number 23 and 28 here in the map, that have a really high output. So they both produce only from one well 20 megawatt electricity. And I wonder why we can't drill these wells first, why we just can only drill those wells. And maybe probably the red ones, few of the red ones. But why do we have to drill first like 25 wells and then find these most productive wells? So this is a bit of my motivation. And I said, this is only one field. This is the statistics shown in a different way. So well capacity on the x-axis from 0 to 20 megawatt. And you see that 0 capacity has the highest abundance. These are the world statistics. So if you put these small blue statistics into a worldwide use this ICP report, which I can share with you, or you also, if you're in geothermal research, can go back to your field and try these statistics also with your field, you will come up with a similar statistics. So most of the worldwide wells drilled have a capacity of 3 to maybe, let's say, 4, 5, 6 megawatt output, but the wells with really high output, like 15 to 20 megawatt electricity, there are only a few of them. So I would like to ask a question. I hope that works with our chat function, or just let me know, shout out what is your idea. I would like to ask you, where would you drill the next well in this field? So I invite you to type that probably in the chat, or just unmute yourself and tell me your idea. Try to open the chat as well. So there's one answer in the south. Few of you would like to drill in the middle with a question mark. Also, I don't know. Yeah, okay. So I think most of you vote for the middle. And I just guess here now that you saw that the green wells are located basically in, someone wants to drill in the north. Yeah, also that's fine. For another try north. Okay, so most of you I see in the chat that are voting for the middle of the field, the central field, to drill another well, probably close to the green ones. And if you continue the story, I think I have to give you a bit more information. So you see people want to drill north, south, and middle, but it's easier, of course, to decide that if you have a bit more information than only this topographic map. So let me introduce to you a bit of the field. So that's the structured geological map. We see a strike slip system with some overlap. So we have extension basins close to the lake, for example, where you see there's crossing faults also in the picture. We have some, therefore, because of this overstepping, we have thrust faults and also normal faults. You see a thrust fault quite nice here in the picture on the top left. So we did that field work and we came up with the structured geological map. So that would already help you to probably better define your drilling target. Then also there have been MT studies. So this is an MT cross section towards northeast, so southwest, northeast, basically crossing the lake also. You see the lake here. That also cover the two really productive well area. So we see that the MT found that the upflow zone is below this lake. So this lake was already an area of interest for us and also for you probably because you want to drill in that area. And also you see that the productive wells in general are quite close to faults. So that's the outcome of this map and a bit of geophysics. Then I would like to give you some information on the geochemistry. We have been sampling from wells and also from springs. And the final result of that sampling over several years is this hydrogeochemical map. We have two systems, two fluid systems basically, and one of the system is an acidic system, which is marked in green here. And you see another study from a colleague of mine on corrosion potential of this fluid, and it has quite a high corrosion potential, this acidic fluid with a pH of 2. We saw in one well that they had lost 80% of the casing in 1 year only. But then there are also wells here now in blue, which are not that acidic. So they have a pH of 4 to 6, which is quite neutral for these volcanic high enthalpy systems. So two different fluid systems, and you see they are separated by faults. They don't mix. So quite close, if you sample from wells which are really close to that fault, we have really different fluid properties here. Then we also did discharge measurements in rivers, which is a bit unique for geothermal research, but I can say it's really helpful. So we not only have this lake, of course, that lake has an inflow and an outflow. So we measured the discharge, the volume of water flowing in that river at different points, upstream and also downstream, to compare where this water actually coming from and flowing into the lake, and then also how much is flowing out. For that, we just used the simple technique of salty water, NaCl, rich water, which we put into the stream, and then we sampled it with a tracer curve, just using the electric conductivity. The outcome is a bit surprising because normally you have a smaller upstream than downstream. And also here, this general trend we still see. So you see that upstream we have 44 liters per second, or then 39, compared to downstream behind the lake, that it's about 60 to 70. What is surprising is that the flow, the discharge in the river changes across the faults. So it's not only increasing, but it's also dropping in between. So it drops from 44 to 39, and then behind the lake, it drops from 76 to 64. This is not normal. Normally the streams and the rivers gain water going downstream, but these also lose water. So that means that and I have that here again, so that means when the river or the stream, it's quite a small river sometimes, crossing these faults, which I mentioned before are normal faults, they lose up to 12 liters per second, which is quite a bit. And this is only possible by measuring really this with this tracer test. And we not only see this in the rivers, but we saw that when studying the reservoir data, the well data, we put together this consumption model, and then also we modeled in a cross section on the top right the temperature distribution, and we see that here now shown with a red arrow, this is a fault upstream of the lake, and this is the fault downstream of the lake, and at least upstream of the lake, we see that there's a cold water inflow into the reservoir up to basically 1.5 to 2 kilometers. You still see that the water from the river, which is infiltrating and which the river loses when crossing the fault, is influencing the reservoir temperature. And we calibrated this with well temperature, and this is nothing you want to have in your geothermal reservoir, but which is obviously happening. So we have a cold water injection here, a natural cold water injection into the reservoir, influencing the reservoir temperature. Also, on top of that, we learned that, you remember from the hydrochemical model, that there was a fluid barrier between these acidic fluids and the neutral fluids. So that fault was actually a barrier. The fluids were not mixing. But here we see that the same fault, again, is a conductor, because it allows the injection of that river water, that colder river water, into the reservoir up to that well depth where we see that. So this is the first kind of conclusion or first step of that project we did. It was a research industry collaboration. We had several field campaigns which were funded with a few million euros from the German government and also Helmut Center in Germany. We were an international team. It's quite fun to work with the partners in Indonesia. And also I have one ongoing PhD study on this, which looks into these aspects a bit more in detail. So my next question to you, what I'd like to pose this, so now that I gave you a bit more information, again, I would like to ask you, where would you drill the next well now? If we go for the central area, in which direction and where exactly would you place the well? If you have now the information of fluid types, of faults, of productivity of the wells. Can I have some ideas from you? Again, you can just unmute yourself or type it in the chat. I see one suggestion southwest of the lake. Any other ideas? A lot of question marks. Yeah, it's tricky to know. I like that answer. So south of the lake, southwest. Again. South of the lake, but north of the fault. So still within this kind of small extension basin, as I understand. Okay, thank you. Thanks for the ideas. Let's go a bit further. I like the idea that it's still tricky to know, and that actually triggered also our next step in our research. So I think for now, we understood that this lake, and it's called Lake Linau, has a special role a bit. Also, I can tell you that the fluid, that the water in this lake has a pH of 3, which is also a bit special. So we have an acidic water even in the lake. And you remember that along the near to that lake, we sampled from acidic springs, from acidic wells, but still the wells tapping below the lake, they are the most productive wells in our field. So we wondered in this next step of our research, that's called the LOLA project, that why is the lake water acidic, and also is there a hydraulic connectivity between the lake and the reservoir, because we see the same fluid type in the lake and in the wells. And also on top of that, in a more long-term approach, why are these wells so productive if we drill beneath the lake? So what we did is renting this small raft here, this small boat, and the driver on top. We installed a few instruments and we did a bathymetry study of that lake. You see on the left map how we drove on the lake, so basically in circles, which went smaller to the center of the lake. And then you see we crossed some parts of the lake a few more times, especially the locations which I labeled was C11 or G1, because they were interesting for us. And that you see on the right map. So the right map is basically the bathymetry map, the depth map of that lake. It's basically the topography of the lake, and you see that it's shallow and not that steep on the eastern side, also on the north. But then on the western shore, you see that there are some deep areas up to 30-meter deep, and they are also kind of aligned along the western shore. And the western shore in general is quite steep. If we put this into a 3D picture, you see that that there are actually holes in the lake. So you see that the lake has a depth of about 10 to 12 meters on average, but then we have deep holes on the western shore which go up to 30 meters deep, and they are not very large, but they are really like have a cone shape and are like needles going down in the subsurface. And we were also able to take sonar pictures, which you see here, the brown pictures in the middle, which show quite nicely how these holes look like. If you look at the top left, there you see some manifestations, what we call hot spring areas, fumaroles, really altered areas. And these volcanic areas, you have this steaming ground, bubbling hot springs, and these are labeled here with this orange color. And you see that they also mostly appear on the western shore. So we had the idea that also now taking into account the structural geological map we had mapped before, that there must be a relation. And at the bottom picture, you see that we were able to map some faults. If you then zoom in, that's probably not that clear from this small picture here, but if you zoom in, you see the alignment in the topography of the lake. There are some kind of rifts and basins which show us that there are some faults crossing this lake, which is quite normal. It's just that we have none of that because nobody looked into the lake. It's like a blank map, a blind spot here. So what we did on top is geochemical measurements in the lake. You see again the map with some dots now. So we put a rest basically on top of the lake, and we sampled from 52 locations. But I only want to show you a comparison of 4 of them, and especially the deep holes. We were able to stop the raft exactly on top of these deep holes and lower down our instruments into the holes and measure different parameters, which is temperature, electrical conductivity, so salinity basically, the density, and also at some locations we took samples and were able to measure the pH. So these samples were, the measurements with this orange sensor were taken every 15 centimeters. And I want to draw your attention to the profile on the very left, the G1. You see that actually in all profiles that the temperature, for example, the blue line is decreasing by depths, which is quite normal for lakes, right? So at top you have a warmer water than at the bottom. And then if you continue, but then in G1 especially, you see that from 15 or 17 meters on, the temperature is increasing again. And it gets quite bumpy. So you have several peaks here in the line of the temperature, the blue line. Then if you look at the red line, the conductivity, salinity, also that one is first decreasing. Also you see that trend in all profiles, and then increasing a little bit. It's not that clear, but you have a different layers in these lakes, which is also quite normal. But then again, if you look from 17 meters on, it gets more bumpy again. You see several peaks, strong peaks here. And if you would zoom in, you would see that the peaks of the temperature and the conductivity, they align quite nicely. So if the temperature goes up, also electric conductivity goes up. On top of that, you see the green dots. These represent the pH. And if you look at the pH at the lake surface, it's still high, and then it's decreasing. Although it's minor, but we see a trend of decreasing pH, increasing temperature, and also increasing electric conductivity. And we already published this, so you can see and read all the details in our paper. Our interpretation of that pattern is that we have a water inflow into these deep holes. So we have a water inflow at these blue arrows where the peaks get up. We assume that there's a kind of permeable zone in the deep hole. So you can think of the deep hole being here next to it, a deep hole where there's a permeable area, a permeable rock, where the hotter, at least hotter than the lake water, and more saline water and also lower pH water is flowing into the lake, which would explain the kind of hydraulic connectivity between the reservoir part, the geothermal waters, which are below the lake, and the lake itself. So summarizing this part of the research is that if we integrate all the data, the map on the very left is our knowledge from before. We knew there are some faults onshore. We had the assumption that there might be a fault crossing the lake. After the bathymetry study in the middle, we were able to map faults, including faults onshore manifestations, and the bathymetry, the depth measurements. We were able to measure or to align these faults, all of them, and using the geochemistry, we were able to also find inflow areas into the lake. So where does the hotter and saline water, low pH water flows into the lake, and a bit further, which you can read then in the paper also, allowed us to draw conclusions on the permeability of the faults. So which faults are more permeable, which are less permeable, where's the inflow, and then also explain why the wells are so productive, because they cross quite permeable faults. And also maybe one major point here is that you see if when the faults are crossing each other, so intersection points of 2 or even 3 faults like here and here, are exactly the locations where the deep holes are located. This all is validated against a database which we have from the wells and springs and outcrops, our fieldwork, over 8 years now that we do research in this area. Maybe just a small comment on this. This is also published by now. It's basically a proof of concept. So we use the same method in a volcanic lake in Turkey, which is called the Nali Lake in central Anatolia. You see the lake, and also here you again see from the bathymetry study on the bottom left that we have deep holes in this lake as well. And here we were even able to picture some outflow from the deep holes. So this is one of the deep holes, the deep hole number 1, what we call it. And you see that there are bubbles coming out of this deep hole. And you see the bubbles also in this profile picture here. So that is a proof of concept basically for our new technology, new method, new approach that we suggest to use in these volcanic environments. The impact of the results is quite clear. This company continued drilling using also our data, our new findings, and they were able to drill about 10 new wells, which you see here at the bottom. And we were able, together with them, to increase the drilling efficiency by about 15%. So the 10 wells or 12 wells they drilled, more than half of them were successful now. So they had a much better understanding of this field at the end. I will skip this. I will just want to mention that also we do hydrochemical monitoring. I mentioned that we work in this field now over 8 years. And we see that the operation of that field, which is ongoing now for 15 or maybe even 20 years, is affecting this field. So we see a change in the hot springs. First of all, in the chemistry of the springs. Some of the neutral springs, which were off the center of the system, are now also turning into acidic springs, and also the physical appearance of the field of the springs is changing. So one example is here on the top, left and right, where you see the same spring, which is decreasing in size, basically. So it does not have that much discharge anymore. And we suggest that this is due to the long-term operation in this field. This is a short insight into the PhD study of Lily. She is now integrating all the data we have from over these 8 years of measurements. she's putting this into a 3D model, and you see it gets quite complicated when you combine temperature data, alteration data, outflow data, also the feed zones of the wells, which you see at the top left as these yellow boxes. We try to understand where is the system kind of fed from, where is it taking the fluids from, and how are the fluids flowing in the underground. So her next step is bringing these conceptual models into a more dynamic model and modeling the fluid flow in the underground. So with that, we want to understand how we can sustainably use this system in a better way, and how we also with the operation influence the surface features like the hot springs, the outflow, and also the geochemistry. With that, I make a small break, and now I only have a few minutes left. I will keep it short, the next part. I just have some impressions from our fieldwork. It's quite fun to work in geothermal research with large teams, with international teams. I really invite you to have this experience. Get in touch with me if you're interested. We can maybe do something together in future. I also had an accident during our fieldwork, but this is just a minor issue and part of our work nowadays also. So I want to mention a few things on the second topic, which is how to operate sustainably. What did we learn from different field studies here? And I would like to start with this very typical example again, where you see productivity and injectivity indices from different wells. You see two curves, a red one and a black one, and you see that they start high up, different still, but still both of them have basically a decreasing trend, and they show the injectivity of these two wells. So that system which we are talking now about is a basically low to middle enthalpy system located in Lithuania, and was operating for since 2001, I think 2002 they started producing first from two wells, and now only from one well, and then using the heat to heat the city or part of the city of Klaipėda, and then injecting the water again back into two wells. The story of that they first used two production wells and then only one already explains the problem. The injectivity decreased so much that they had to stop the one production well because they couldn't inject the water back again that they produced. So productivity is quite high, which you see also here. The black and the red dots are the productivity from the two wells, and the black and the red line are the injectivities, which is quite different. So there's a constant decline. It was not recoverable as stimulation. So the blue arrows show different stimulation techniques like acidification, mechanical cleaning, drilling a sidetrack, drilling radial jets, cleaning the whole system and refurbishing it. So all of that did not work out until the very end. They had to stop the power plant because it was just not working anymore. We did quite detailed studies on the reservoir rock properties. We thought that might be the issue because there's maybe too less porosity, but actually our porosity measurements showed that there's porosity in the sandstones of 26.1%, which is really high. We measured also the pore sizes. 85% of the pores have a size of 3 to 40 micron. And I marked this in red because I want you to remember this number. Also, the permeability of these sandstones is quite high. There are some clay layers in between, but all of our studies and the GFSAT lab and the ETH lab showed that the composition and also the pore distribution is quite favorable actually for production and also injection of fluids. The reservoir fluid properties also seem to be quite stable. We have a basically neutral water, which is quite saline. It's one of the oldest groundwaters in the world. There's a special publication on that even. And also it did not change over the years, not much at least. But we took a sample from the well, and I put it into this glass bottle and took it out, put it into the lab and took it out after 1 year. And you see on the left picture that we have some precipitation within this water without doing anything. Of course, it has been in contact with oxygen, but still there are some really huge gypsum crystals here. And at the bottom left, you see an example which they have still in the power plant in the exhibition room. This is a gypsum crystal sample, basically, from a pipeline, from a surface pipeline. They took out and cleaned all these pipelines. And this only took 2 years of operation. And then the pipelines were clogged up to 6 centimeters and there was no flow anymore. So they had to stop the power plant and clean everything up. So we came up with this vicious circle, what I call it, what they have been doing here. And where I always invite the geothermal operators to start early talking to geothermal researchers, because you can avoid and understand some problems in advance before facing them, actually. So I explained to you that they faced really huge precipitation problems here in the pipes and also in the wells. I saw the downhole pumps, which have really gypsum crystals with the size of 20 to 30 centimeters. And they thought to solve these problems mechanical cleaning and also acidification. So they cleaned the wells and everything was clean. We checked that with this, you see in the picture with a small camera. Everything seemed to work again. But we also took samples from the filters. And the filters have a size of 1 micron. So they are normally filtering the water before it comes down again. And what you see here is that the grain size distribution before filtering the water, they are still particles which are bigger than 1 micron, which is quite normal. Also, you see that it's a mixture of magnetic particles, which are basically an indicator for corrosion of the pipes, which is also not that good, but also kind of normal. You always see this in geothermal power plants, but also reservoir materials, so small sand particles, basically produced up from the reservoir. When you compare this grain size distribution before the filters with after the filters, which are now here bigger, you see that again, in the fluid, there are particles which are larger than 1 micron, up to 40 micron or even 60 micron. This should not be the case. So this is an indicator that the filter, which is 1 micron, is not working. So it's not filtering out the large part, the larger grain particles here. So they're introduced into the reservoir again. And in the beginning, I told you that the pore sizes, from 85% of the pores, is 3 to 4 micrometers, 3 to 4 T. And also the grain particles here now we see in the fluids have a size of 3 to 40. So that's a perfect match with the pores that are waiting for the fluids to be injected, but the fluids come with the grains, with particles, and they basically block the pores immediately. So with the acidification of their system, they also triggered fines migration, which is not what they wanted. So they, at one point, decided to use an inhibitor, which inhibits the precipitation of gypsum perfectly. So they don't have any problems with gypsum precipitation anymore, but they could have avoided the problem of fines migration here. Then we did additional studies on the microbiology. We studied this. We had some numbers on cell counts, on production side, on injection side from different years, and you see that both of them increased over the years. We also investigated the filters, which basically look like this. So you inject the water here, and then it's coming out here again, filter basically. And you see that before and after the filter, the DOC, so the dissolved organic carbon in the water, is increasing again. So it's from 1.9 to 2 and 2.2 to 2.4. It's not that much, but there's an increase of organic carbon in the water. And also we took one slice of these filters and put it into the water, stirred it for 2 days and then even for 1 week, and you see that the dissolved organic carbon is also increasing during that time. So that is an indicator that this filter is also releasing some organic material, which is not wanted if you know that you have microbial activity in your system. So you're basically feeding them. This is also the case for the inhibitor, not only for the filter, but also the inhibitor is made based on organic compounds, and this is feeding your microbial system at the subsurface. So you have in your filters, then these are the filters we used with 0.1 micron. You have this slimy organic filter residual. And not only that you have the problem of biofilm in your system, this microbial activity is also causing corrosion. And therefore you have this magnetic filter residual always in the filters also. So this is a vicious circle, what I call it, because there's no out at the moment, but there are some steps that could have been avoided, that could have been understood before they take action, actually. So you as researchers and the other party as operators, please get in touch and talk to each other, help each other to avoid these problems. That is actually also the topic of a PhD study from Anna. She looks into that problem a bit more in detail within the Easygo project David mentioned in the beginning. So she tries to understand in a more general way the reasons for injectivity decline. She came up with this kind of flow chart where we find the problems, what are the problems. She's now investigating on lab experiments we can do to better understand the problems. I just drew up, she has studied the literature extensively and came up with this matrix, which is of course not readable for you, also not for me, but she plots clogging processes against parameters like pH, salinity, and density, and then brings these parameters and the clogging processes together to understand what is happening here, why is it happening, and can we rebuild this in the lab to better understand and then in the future avoid this problem. David mentioned the Easygo project. I'm the PI of this research project funded by the Marie Sklodowska-Curie action within the EU. It's an innovative training network within the IDEA League with 4 universities, 4 different countries in Europe. We have 10 industry partners and could fill 13 PhD positions. We work along large infrastructure. All of these universities have access to large infrastructures, which are geothermal wells, which are geothermal power plants, which are underground real scale lab. And with that, with the combination and collaboration within the industry and the universities, we will be the first ones who provide a generalized education, including joint degrees in geothermal research in Europe. We work on, again, 2 different questions. How do we run geothermal systems efficiently and how do we run them safely? We therefore have these 13 positions you see here along the whole chain of geothermal energy, which is some of them focus on the reservoir, some of them on the production side, some on the injection side, some work at surface, developing surface monitoring concepts. Some of them work on developing components, sensors, also on the power plant. So some of them work on increasing the efficiency of the power plants using these binary cycle power plants, for example, but also working on the turbines. We not only provide the students with a content-based education on geothermal energy, but also we develop for them what we call personal development staircase. So they get a training in soft skills, transferable skills, how to work in teams, how to self-manage their research, what is open science, how can I be creative, how can I gain from collaborating with the industry also. There I want to give you one more example. From Nicolas, you saw in the beginning, he is working on a new concept, how to better use EGS systems. We often see that also these EGS systems face clogging problems, clogging and precipitation of minerals in the system itself, in the reservoir, but also in surface pipelines. And we, together with Martin Saar, we had the idea that we use CO2 basically. So Nicolas is investigating this idea developed by Martin Saar using CO2 as a replacement for water and geothermal systems to avoid, in this special case for EGS systems, to avoid clogging problems. So this is another aspect of our geothermal research at DTH. I will stop that and thank you for now, because I can guess there are some questions and I look forward to your questions and maybe a discussion. Thank you.
Thank you so much, Maren. That was really great and interesting. Do we have any questions for Maren?
I also invite you to get in touch anyway later on if something pops up. Just get in touch with me right now.
We have Janine, got a hand up.
Oh yeah, no, it was a really interesting talk, Maren. Thanks so much for telling us about your work. I really like the sort of multidisciplinary approach that your team are using, and sort of thinking about sustainability as well. I guess so. As a volcanologist, it's sort of quite out of my field of expertise, but also really interesting to sort of learn about the possibilities of what can be done. And in our group, we're modelling fluid flow, but our fluids are magmas moving through fractures. And so I wondered what you thought about in these systems. What's the role of new fractures being made as fluids are moving around compared to exploiting existing fractures? So is there a way that we can get a handle on what the role of new fractures being made by the fluids moving around is compared to just exploiting existing fractures that are there for other reasons?
Yeah, so just to really understand what you mean. So creating new fractures in a geothermal system is only possible by introducing a lot of pressure. And this is what we call hydraulic stimulation. I'm not sure if you meant that one or if you mean the fracturing by magmatic bodies probably, or maybe cooling and heating from the underground, or because because the geothermal fluids, if they move around, they will not open up new fractures. They don't have that kind of power or not that much pressure in the system. So we would introduce artificial pressure from above through the valves. This is done. Yes, this is done. This is the so-called hydraulic stimulation technique, which is widely known, I think, which is related a bit to the issue of induced seismicity, a whole other research topic. Saying, I don't know, you want to comment on this or still? Or?
Yeah, so I guess it's the sort of, I was wondering about the difference between fluids moving through those fractures which are like artificially induced compared to the natural fractures. I don't really have a good understanding or idea about how those different ways that fractures are made might affect the way that fluids move through them.
Yes, I see. Okay, so well, a fracture is a fracture, but the artificial fractures are, the problem with the artificial fractures is to keep them open. So if you introduce that high pressure through the valves into the system, you might create fractures, or you might open up closed fractures. So open up existing, but maybe blocked or kind of, closed fractures. But then to keep them open, if you release the pressure, because you will not always have this pressure in the well on the system, that is an issue. There are also techniques like including within pressurizing the system, you also inject small particles that are that are intruded into the fracture and that they keep open the fracture. That is first of all the question if there's flow in the fracture or not at all. Other than that, I would say in freshly opened fractures, the flow is much easier because there's no precipitation. It's a basically open pipeline, if you want to say so. Other than that, there's the question of how far can you go with creating these artificial fractures. So this is still a question mark also for me. How far do these fractures really go, and how can we measure this? People try to understand this with microseismicity, but there's also a big question mark if this is the right technique to really trace the fractures that you introduce, because they can be so small you can't measure them with microseismicity even. So I always am a supporter of using the natural system. So also in terms of the fractures, I really support of that we better understand the natural system as it is and not focus on how we can change it, because maybe it's a kind of belief question. I don't believe that much into this. these big techniques. You can do something, but still, I always say that the natural system is much better, much more efficient. That also in terms of fractures, I would say.
Great, that's really interesting. Thanks so much.
Great, thank you for that. Is there any more questions? Do we have any? Oh, Caitlin's got a question. Go ahead, Kate.
Thanks, Maren, for a really great talk. I was amazed that you do experiments over the course of a year. But my question is, I might have missed it when you were speaking about it in the talk, but when you know the location of the deep holes or where the faults intersect, then how does this link back to knowing where to drill next?
Yeah, so yeah, good question. Maybe I was a bit fast in that moment. I tried to show what we knew before our studies. We just saw the lake, then we added the fault locations, and then the question is if the fault is permeable or not. And if the fault is permeable or not, we can understand by relating them to the deep holes. So we saw that the deep holes are where the faults intersect. So we know the fault, if the fault itself is not permeable, at least the intersection point is permeable, because there's fluid is coming up and fluid is rising into the lake. So at least we know at the intersection points there is fluid flow. And then if you then think a step further, you question where to drill next, then I would rather go where the fluid flow is. So if you're not sure about the fault section, if it's permeable or not, but you see the intersection point is permeable and there's fluid flow, then drill close to that point, especially in these volcanic systems. There you know that porosity is quite low. So we really rely on fractured systems, fractured areas in the volcanic rocks. And they are most probably where faults intersect and where we already see fluid flow.
Okay, thank you. I understand now.
I hope that answered your question.
Great. Dan's got a question. He's got his hand up.
Yeah, hi. So yeah, my question follows on nicely, I guess, from your answer to the last one too. So I just wanted to have a bit more detail, I guess, about the host rocks to these faults in these areas as well. So they're in volcanic materials and they're typically low permeability. Is that right? Before these faults cut through them.
Exactly. So we are in the rocks are basically breccia, volcanic breccia, and andesites, some tuffs. We see. And we took core samples from that and also outcrop samples, but we also have core samples from the wells. We did permeability measurements, and permeability is about 10 to the minus 14 square meters, which is really low. And also porosity is about, I think, if I remember correctly, about 10% or so. So we really see the need of going to the fractured areas to produce.
That's interesting. Okay, thank you.
Yeah, you're welcome. Thanks for your questions.
Great. Maybe I'll ask a question, if that's all right. So within the industry that you work with your partners, I just wanted to get an idea of how often the geochemistry of the fluids are sampled, and whether these companies, do they have to do that legally, and then provide them to the researchers to get studied and investigated?
Yes, very good question. That would be very nice if they would do that for us and give us the samples. That's not the case. How often they sample is, and how often they do have to sample is really depending on the country. Anna, I mentioned, when she studies this injection problem of geothermal power plants, she also looked into legal and administrative regulations in different countries, at least in Europe, and they are really different also concerning injection, if the operators have to inject at all, or if they also can just discharge the produced water. That even is quite different, and also then the kind of reporting they have to do is really different between the countries. So what I experienced in the high enthalpy fields I studied in Indonesia, they sample from time to time, let's say maybe once a year, twice a year. And they only check the basic parameters, like probably major ions, but only physicochemical parameters. If they want to share the data with us, it's really depending on if they see a benefit from our research. So if you can make that clear, they are willing to share. If not, they are not sharing. So we always come equipped with our own sensors and measurement and sample bottles. So all the data I showed you related to geochemistry, these are our own data. I know from other companies, for example, and I studied with a company in Netherlands, they sample their wells, I think twice a year, once a year, twice a year again. And they have a kind of ready database, and they were happy to share that with us. So we study that together. It's so different. I always come prepared with my own sensors and sample bottles, because you never know what happens with the operators, if they see that benefit, if they're afraid of releasing data and so on.
Okay, thank you. Maybe just to follow up, do you think that the government should be doing more of a job to sort of make the companies do these samplings, so then we can understand better how the precipitation and the clogging of these reservoirs happen?
Well, I think I don't see the government here. I would rather go maybe a bit more general for public information. So also informing the public, but also informing maybe the companies, or do a bit more of the communication between the researchers, the public, and the companies. So the companies also see the benefit of doing sampling more often. That would be one part. Then also I often see people, friends, even family, saying, oh, I didn't know that geothermal is that advanced, and we already have geothermal production in certain countries in Europe, and now in Germany, for example, in Munich, they have a lot of things going on, and people are not aware of that. So I would rather see the government's responsibility in here communicating that. And I think what you mentioned, this regular sampling, the sharing of data, that is then kind of naturally coming up, might be the next step, probably. But I also see, when working in the Netherlands, they have a database for collecting data from different geothermal reservoirs, also hydrocarbon reservoirs, which you can access easily. Not all data are in there, but this is the first step, which I really enjoy, and the researchers enjoy, and they are kind of attracted by the Netherlands because there's data available. So it's... Yeah, but I see the communication part in advance, so that people themselves are convinced to do that and not forced to do it.
Yeah, that's really great. And if you wouldn't mind maybe sharing a link to that database for us at a later date, yes, that'd be great. Fantastic. Do we have any questions on YouTube? Janine or Caitlin? No? Okay, any more questions here?
I type it in the chat before I forget. I think it's called the NLog database.
Okay.
If you Google for that, you should find something.
Fantastic.
If not, get back to me.
Okay. So if there's no more questions, I guess we'll leave it there. Thank you so much, Maren, for that really interesting talk and for answering all of our questions. It was really great to hear what you're working on. And I hope maybe we can have you back sometime soon to see what any updates in the geothermal space in Europe. That'd be really great.
Definitely, yeah. Just let me know. Get in touch. I'm happy to keep in touch. Thanks so much for having me this afternoon.
Thank you very much.
Interesting.